Hi guys, my name is Mark, and today we're going to be looking at the higher level 2022 chemistry paper, and particularly going to be looking at question 4, which is a multiple choice question and is worth a total of 50 marks. So let's get straight into part A, and then we're going to have a look through all of the different parts. So, I highly encourage that you do as many of them as you can, because it's really easy, really good place to pick up marks. So yeah, let's get straight into part A. So just before I launch straight into part A here, there's just a few things to know about question 4 on this chemistry paper. And the things to know here are that it is multiple choice, as I said, and you have, I believe it's 8 parts that you need to answer, but there's obviously more than that. So you have a little bit of space to kind of pick and choose what you want to do, but I highly recommend that you give all of them a good rattle, because you're going to get, if you make a silly mistake or you accidentally leave out something, or if you just end up being wrong, if you do a few extra ones, they'll obviously pick your best kind of set. So yeah, we're going to have a look at each of the parts and hopefully kind of give you a little bit more of an explanation of what's going on, how I'm tackling the problem. And yeah, let's get straight into part A. So part A here is going to be a question on kind of the history of chemistry. We're going to be looking at something known as a Dobereiner triad. So it's kind of an important part of the history of the periodic table. In this case, we're told that there's a set of elements, Li, Na, and K. So in this case, Li is lithium, Na is sodium, and K is potassium. And we're asked to refer to this example to explain, so we're going to be explaining something here, to explain Dobereiner's contribution to the development of the periodic table. And as I was saying, this plays into kind of like the history of how we got to where we are now with the current periodic table. So jumping straight into the answer here, what I've written down is that Li, Na, and K, or lithium, sodium, and potassium, all have similar chemical properties. Another thing that we need to note at this time is that they also have kind of an important relationship coming from their atomic mass numbers. So the atomic mass number of Na in this instance is the average of Li and K. So basically what it means is that central, if you look here, they kind of come in pairs of 3. That central one, in this case Na, is going to be halfway. It's going to be that average between the lithium's atomic mass number and also the potassium's. So that's another important thing that Dobereiner kind of discovered, and that's why he arranged elements into these little groups. They have chemical properties that are very similar, and also that there is kind of a relationship here between the average of the atomic mass of lithium and potassium are going to give you, in this case, should I say for this example, the atomic mass of sodium. So nice straightforward answer here, and if you wanted to kind of take this a step further, you could even like write it out, prove this. In particular, that last one about the average, you could actually write down the atomic mass number of lithium, and the same for potassium, and then add them together, divide by 2, and you'll actually find that it is the atomic mass number of sodium, which is kind of exactly what he had, one of the reasons why he had grouped them. But in this case, in terms of marks and where they're coming from, there was a total of 6 marks going for this question, and they were broken down into kind of getting two reasons, in this case, contributions, and kind of, to explain them. So in this case, the first one here is going to be saying the note that we made about having similar chemical properties, and then you've got another 3 marks for mentioning this fact that the averaging between the Li and K in this example gives you the atomic mass number of sodium. Moving on to part B now, we're asked a question about the Balmer series and kind of hydrogen emission spectrums. So in this case, what we're told is there's, red light. In this instance, it's one of the lines on the Balmer series of the hydrogen emission spectrum. And we're asked a question relating to photons. And it's, why is a photon emitted as the electron moves from one energy level to another? And this is shown in the diagram we have here on the right. And what I'm going to do is going to write out my answer here, and I'm going to take you kind of through it, giving a little more context as to what I mean. So here is my answer. I'm going to kind of just go through it. So in this case, an electron in the outer energy level is in the excited state. So basically, whenever we have electrons that aren't in their ground state, which is kind of how they are normally, when there's a little bit of extra energy associated with them, they're going to be in this outer energy level, also known as the excited state. And what we know is that when this electron is in this excited state, it's going to have more energy than an electron in this inner energy level. So the inner energy level is actually known as the ground state. So electrons in the excited state have more energy than those in the ground state. And moving on from this, this kind of means that as an electron falls, so kind of this is an important part of the answer here, as an electron falls from this higher energy level actually to a lower energy level, what happens is that energy, the energy difference has to be released. And this kind of relates back to the start of the question where we're asked, about this photon. How does the photon come into this? Well, when energy is actually released, what we know is that that energy is released, but it's actually released in the form of a photon, which is actually exactly what we're kind of required to explain here. That energy falling from that higher excited state down to that lower ground state, the energy difference that's released in the form of a photon. And there's actually a formula that we can use to model that, which is this one down here. So just to kind of give it a little bit of a squiggly line, E2 minus E1 is equal to HF. And just to kind of, a little bit more of an explanation behind that formula, E2 is kind of the energy associated with the photon when it's in that excited state, and E1 is the energy associated with the photon in the ground state. And as you know, there's more energy in the excited state than the ground state. As it falls, that difference in energy is going to equal to HF, and HF in this instance is how we model the energy associated with that photon, with that wave. So you don't really need to explain that, but in this case, just kind of using these buzz terms, talking about excited state, ground state, kind of falling between them, and energy being released in the form of a photon, should I say, and even using this formula as well will get you most of the mark. So in this question, there was a total of 6 marks going, and the breakdown was fairly simple. There was kind of, you kind of got all of the 6 marks for talking, including any of these points that I have here. So talking about the electron in that outer energy level, having more energy, one being, when it's in its excited state or when it's in its innermost energy level, and the ground state has less energy, and then really talking about the difference as it's moving between them. The photon that's emitted is actually equal to that change in energy. And if you want to throw around this formula just kind of here, you're going to get, it kind of almost sums it all up. But personally, I would kind of include a little bit more of the context in writing it out, because it helps the examiner understand that you actually know what you're talking about. So yeah, that was part B. Moving now on to part C here, what we're going to be doing, or should I say what we're being asked, is a question on ionization energy. Specifically, why is the second ionization energy of lithium significantly larger than its first? So the way I always tackle these types of questions about ionization energies is I always like to look at the electron configuration, because we can actually, figure out a lot of information and get a lot of insight into what's actually happening once we know the electron configurations. So that's what I'm going to do. So writing down here the electron configuration of lithium using kind of just the methods that you normally would in this case. What we know is that lithium, it's going to have an atomic number of 3, which means there's 3 electrons there, and they populate the 1s orbital and the 2s orbital. In this case, we have 1s2 and 2s1 is kind of the arrangement, and this actually tells us a lot. And I'm now going to use this information to properly answer the question that we were being asked, which is why is the second ionization energy significantly larger than that of the first. So taking a closer look at this electron configuration, what we know is that the second electron actually comes from a full shell, and kind of how we know this is when we do the first ionization energy, taking away that first electron, we're going to be taking away from this 2s1 orbital, we're going to be taking away that 1 electron, and because that is not a full shell, because it's not perfectly stable, it's actually a lot easier to take away, which means that first ionization energy actually isn't massive. It's it's not as high as you'd kind of expect, because there's already an electron missing, so it's not perfectly stable. But coming back to our answer here, we were saying that the second electron actually comes from a full shell, and what this means is that the electron, when the electron is removed, it actually takes a lot of energy to overcome the stable arrangement of this full shell, because as we know, electrons, they like to be in stable arrangements. We have the octet rule and lots of stuff kind of like that. And in this instance, because it is a full shell and we're removing the second electron, it's a lot more difficult to do so. So when we're looking at that first electron, we see that it actually comes from a shell that isn't full. And kind of going back, we were kind of talking about it earlier, it's this 2s1 here. It actually isn't a full shell, and it's actually very easy to remove it. But going back, when we're actually doing that second ionization energy here, we have a 1s2 orbital, and that's full. That's, those 1s2 orbitals, or should I say s orbitals in general, can only hold 2 electrons. And because that's a full orbital, it means there's a lot of energy required to actually pull one of those electrons away, because it's stable and it doesn't want to actually, change. So when we're pulling one of those electrons away, we have to overcome an immense amount of energy in order to kind of do that. And that is kind of the reasoning behind why the second ionization energy is actually significantly larger than that of the first when it comes to lithium. So in this little paragraph here, I've kind of given a little bit of an explanation, as to why this is happening. And I touched on it coming from the standpoint of the second electron being removed and also from the first electron being removed. And it's kind of important that you include it. And once you include a lot of these buzz terms, the total marks that you'll be awarded in this instance are 6. You can explain this using a couple of different ways, but preferred and probably the easiest way to remember in this case is by using that electron configuration like we did at the start. But you could also mention things like the second electron not being as shielded, should I say, from the nucleus, and things like that. But in this instance, using the electron configuration, personally, I found was the easiest way to explain this difference between ionization energies. Moving on to part D here, we are asked a question about flame tests. So in this case, we're asked what color is observed in a flame test on salt of lithium and copper. And unfortunately, these are just kind of things you have to learn off. You kind of cover these when you're doing electron configuration because they're quite a visual way of understanding that. And in this case, we're just going to have two very simple kind of almost one-word answers, and I'm just going to write them down now. So in this instance, the correct answers needed for the flame test, the color seen when we mix lithium, was a crimson color. Now you could also just say kind of plain old red, but crimson I always found was a little bit easier to remember because it was just a little bit different. And for the second one here, we're asked about the color associated with the flame test on a salt of copper, and in that instance, the answer is kind of this bluey green. You can also say green, they're all kind of perfect explanations. And in this case, unfortunately, you kind of just have to learn off these colors. Now there's a few more colors that you might need to learn off for a couple other salts, and I highly recommend you do so. In this case, there was a total of 6 marks going, and the breakdown was fairly simple. You got 4 marks for getting the first one right. So let's say if you got crimson right, and then you got, you said purple for the second one, you get 4 marks. Or if you said, yellow for lithium and you said bluey green for the second one, you get 4 marks. So basically you get 4 marks for the first correct answer that you get, and then you get your final 2 marks for your second answer. So, nice and handy question. Moving on to part E here, we're asked to state Avogadro's law, which is a lovely question if you've studied the gas laws and you kind of remember all of your definitions. Unfortunately, once again, this is kind of one that you kind of just have to know off. There's a few important terms you need to include in there, and we're just going to have a look at them now. So moving on to the answer here, Avogadro's law states that equal volumes of gases, which is an important thing to know here, we're saying equal volumes of gases, while measured under the same conditions for temperature and pressure. So that's the second important thing you have to include. They have the same number of particles, but you could also use a few different things. You could say atoms, molecules, moles, but it's actually extremely important here that you include equal volumes, but you also include the same conditions. So just to underline here, same conditions of temperature and pressure, because you want to measure them kind of in equal and similar environments. So in this case, when we have equal volumes of gases under the same conditions of temperature and pressure, they both have the same number of particles, same number of atoms, moles. Any of those are totally acceptable. So there's 6 marks going for this question as well, and the breakdown was fairly simple. There was 3 marks going for saying simply the same conditions for temperature and pressure, and then you got 3 more marks for saying that the equal volumes, they have the same number of particles when measured under these conditions. So saying equal volumes of gases have equal number of particles, that would get you 3 marks. So however way you phrased it, as long as you included those buzz terms, you get your full 6 marks. So moving on to part F here, we're asked kind of a more mathsy part of chemistry here. We're asked something about moles and grams. So in this case, we're actually looking we're looking at a question talking about one of the largest diamonds that were ever found. And what we were told here is that this diamond had a mass of 1,098 carats. It's a big diamond, and it contained exactly 18.3 moles of carbon. And what we're asked here to do is assume that this stone is, entirely comprised of carbon. We're asked to calculate the mass of 1 carat. A few important things to know here is that we're asked for mass at the very end, and the information that we're given here is we're told the number of moles, and we're also told the element. So this kind of gives us everything we need to kind of make a good start on the question. Whenever it comes to a question like this and it's talking about kind of the mathsy side of chemistry, I always refer back to the kind of important triangles that you're always going to use in these types of questions. And in this case, because we're going to be working with mass, but we're also working with moles, and we're going to be using the moles, mass, and relative molecular mass triangle in this instance. So what we're looking for here is mass, and that means that if we cover mass on our triangle, triangle, it means that mass actually is going to equal to what we have left when we cover it. So it's going to be moles, and this is going to be multiplied by relative molecular mass. And in this instance, we're actually told a lot of this information already. We're already told the moles, and we can actually find this relative molecular mass from our periodic table. In this instance, let me just plug in what we know. So the number of moles here is 18.3, and going back to this relative molecular mass, as I said earlier, we're told that this stone is actually, we're going to assume that it's only made of carbon. And what that means is that it's all carbon, and that, it makes life very easy for us because the relative molecular mass is all going to be just the same. And in this instance, if you refer to your periodic table, what you'll find is the relative molecular mass in that case for carbon is going to be 12. And in order to find the mass now, all we have to do is multiply these moles and relative molecular masses together to give us our mass in grams. So multiplying these two things together, what we're going to find is that there are 219.6 grams of carbon present in this diamond. And we're almost finished in this case. We just need to refer back to the last line of our question here. In this case, it's saying that we're actually asked about 1 carat. So what we were looking at earlier is all of the carbon in this huge diamond. And we were actually told that this diamond is comprised of 1,098 carats. So if we want to find 1 carat, let's just divide this mass we found, this 219.6 grams of carbon, by 1,098 to find the number of carats. So pulling that up here to the right hand side, I'm just going to do some quick maths in this instance. So it's going to be 219.6 grams, and we're dividing that by 1,098 carats in order to find the grams per carat. In this case, if you throw that into your calculator, you're going to find that the answer in this instance is 0.2 grams, and that's kind of what's required here to get the correct solution. For this question, there was a total of 6 marks going, as there is with all of these kind of short questions, and the breakdown was fairly simple. You got 3 marks for finding the correct, amount of grams associated with the whole diamond, and then you got your final 3 marks for finding, the amount of grams of carbon dioxide or not carbon dioxide, I should say, the amount of grams of carbon in that 1 carat that we were asked for. So if you forgot to do the, 1 carat part, and you did the whole thing, you'd only get 3 marks. But in this case, in order to get your full marks, you had to divide by that 1,098 to get 0.2 grams of carbon per carat. Moving on to part G, here we are asked, what reagents are used to confirm the presence of nitrate ions in an aqueous solution? So this is a anion test. There's actually, there's a lot of different ones for nitrates, and some other looking at, I think there's a few that produce carbon dioxide and sulfates and sulfites and all of that stuff. So in this case, we're asked about nitrate ions. And unfortunately, this is kind of just a straightforward, kind of almost like a mini experiment that you kind of just have to know off the reagents that are needed. And let's just get straight into that. So in the case of looking for nitrate ions in an aqueous solution, in order to kind of confirm their presence or not, what you want to do is add iron sulfate with a certain amount of concentrated sulfuric acid, and these can be used together in tandem to kind of test for that presence of nitrate ions. So adding that iron sulfate, so you could also, if you wanted to write that as FeSO4, I believe, so it's, iron sulfate, or you could do ammonium iron 2 sulfate. And mixing that with the concentrated sulfuric acid will give you that, that test for those nitrate ions. And there's a couple other reagents that you might have learned, and they're also completely acceptable. So in this case, you could also have said, and another one of the answers that you could have said is sodium hydroxide solution mixed with a bit of aluminium or copper or zinc. So that also works. In either instance, there was a total of 6 marks going, and the breakdown was fairly simple. You got 4 marks for saying the first part of the reagents needed. So in all of those, regardless of whether you went down the iron 2 sulfate route or otherwise, you always needed to mention, one reagent at the start and then a second reagent used as well. So whenever you get the first one that you get right, and that's worth 4 marks, and you get 2 marks for getting the second one correct. So in this case, the sulfuric acid, making sure to say it's concentrated as well. And in this instance, that's how you get your 6 marks. Moving on to part H, here we are asked to identify a substance commonly added during drinking water treatment. and we have a part I and part II. So in this case, the first, we're looking for a substance that's being added that's going to cause flocculation in the water. So that's the first one. And then the second one is to fluoridate the water. So that's, in either instance, we're just looking for a kind of a substance that can be added. And this is a nice and handy question because there's actually, they're nice and short answers, they're just substances. So in the case of part I, we were asked for a substance that will cause flocculation in the water. And for this, there's plenty of different answers you could have had, but the one I always will go with is aluminium sulfate. And you can also write down the formula as well. That's completely fair. There's lots of different answers that you could have had. You could have had sodium silicate or sodium aluminate, or even something like calcium hydroxide. There's plenty of them that you could have had. But personally, I always just remember aluminium sulfate because it was kind of just the first one that was mentioned to me, and it's kind of the easiest one, personally anyway, to remember. Moving on to part 2 for this question, we were asked about a substance that will cause the water to become fluoridated, and the answer that we were kind of looking for here is sodium fluoride. So it's kind of almost given away in the answer because we're looking to fluoridate the water. So it means there's going to be a kind of a fluorine component, if you will. So sodium fluoride, that works. You can have hexafluorosilicic acid, I believe it's called. Sodium fluorosilicate is also another answer. So there's plenty ones going there, just as long as it includes that fluoride, you're getting your marks there. As with the previous questions, there was 6 marks going, and you got 4 marks for getting your first answer correct, and then you get 2 marks for getting your second answer correct. So in this case, aluminium sulfate and sodium fluoride were the required solutions to give you the full marks. Moving on to part I here, we are asked a question on, I think it's redox reactions. And kind of electrodes as well. So in this case, we're asked what elements are the products of the electrolysis of an aqueous solution that is composed of potassium iodide, or Ki, using inert electrodes. So inert electrodes as well just means they don't kind of take place in the reaction. And this is, I believe this is a kind of like something that you'll cover when you're doing redox reactions. It's kind of something you might see in a Hoffman voltometer, I believe it's called. And let's get straight into the answer, because in this case, there's 2 that you need to have. So the answers required here to get full marks is that when potassium iodide undergoes this electrolysis, and this, using these inert electrodes, what we have created, these products, is iodine, and we also have hydrogen, and those are evolved, so they're just kind of created. Now, obviously, for iodine, you could have wrote I2, or for hydrogen, you could have wrote H2. Those are also totally acceptable arrangements. I and H on their own also kind of work. It's more just kind of showing that you understand the process that's going on. So as with previous questions, there was a total of 6 marks going, and you got 4 marks for getting the first one correct, and then 2 marks for getting the second one correct. So in this instance, saying iodine and hydrogen were the answers required to get your full 6 marks. So moving on to the next question here, we're being asked, which of the following 4 compounds would you expect to have the strongest carbon-to-carbon bonding? And then we're given, the four compounds that we're looking at. So we have ethane, we have ethene, ethyne, and benzene. So let's, get straight into the answer. I'm going to explain kind of why this is the case, and also why the other ones aren't. So for this question, the kind of required answer is going to be ethyne. And I've just kind of written a little answer here briefly. It's saying that this is due to the triple bond present between the 2 carbon atoms. So if we think about ethene, and I'll just kind of write it out. So ethene is going to have a H hydrogen bonded to a carbon, which in turn has a triple bond to another carbon and then another hydrogen. And basically, the more bonds you're going to have, so 1, 2, or 3, the more bonds you have, the stronger that bond is, and that's kind of what we're being asked here, because if we go back to our question, we're asked about which is the strongest carbon-to-carbon bonding. So we go back down to our question here. What we see is in this ethyne molecule, we have this triple bond between 2 carbons, and that's actually going to be, extremely strong, and that's kind of, in this instance, the reason why ethyne wins. Looking at things like ethane is an alkane, which means it only has a single bond between its 2 carbons. Ethene is going to have a double bond, should I say, between its 2 carbons, but that's all beaten out by the ethyne with its triple bond. Benzene is a little bit of a different molecule, or compound, should I say. It's a aromatic compound and has a kind of an interesting arrangement with some delocalized electrons and that type of thing going on, but there is no double or even triple bonds present in benzene either, which means that the winner in this instance is ethyne. Moving on to part K here, we're getting towards the end of the question. And in this case, we're asked about a structure given to us in this little diagram here on the right-hand side, which in this case is aspirin. And what we're being asked here is to calculate the average daily dose in milligrams when a person took a total of 0.146 moles of low-dose aspirin over 365 days. So in this case, we're going to be working with kind of maths and chemistry again. So it means we're going to be using one of our triangles. And in this case, what we're being asked is calculate the average daily dose in milligrams. So this is milligrams, this is mass that we're looking for. And we're told the moles here. So that means that what we're going to do is we're going to be using our moles mass relative molecular mass triangle in order to solve this problem. So throwing down our triangle here, what we're looking for is a mass. So if we cover that on our triangle, what we'll find here is that mass is going to equal to the number of moles times our relative molecular mass. So in this case, we need to multiply the moles by relative molecular mass. What we already know, though, is that the moles, the total moles, should I say, was 0.146, and now we need to find our relative molecular mass. Now, aspirin is quite a large and kind of almost complicated structure because it's actually shown to us over here on the right-hand side, and because we want to find our relative molecular mass, you know, I personally, or I wouldn't expect, or they wouldn't expect, should I say, anyone to understand or know the aspirin relative molecular mass off the top of their head. So now we're going to have a go at actually finding that ourselves. So what I'm going to do that is by counting up all of the constituent parts of this large structure. So I'm going to add up all the carbons, all the oxygens, all the hydrogens, and that's going to give us our relative molecular mass. So just over here on the right hand side, I'm just going to write out, we're going to have a number of carbons, a number of hydrogens, and our number of oxygens. So looking at carbons here, we can actually, we'll start with our carbons. So we have one carbon here, we have one carbon here, we have another carbon here. As well as that here, we're going to have a benzene ring. Now, benzene rings are a little bit special and they have 6 carbons in them. So we're going to have, if you want to kind of put them on the corners almost just for kind of ease of remembering, there's going to be 6 carbons in here. So just write that down. So what we have is 6 carbons in the benzene ring. We have 1 up the top and we have 2 off to the right. So it's going to be 6 plus 1 plus 1 plus 1. So 6 plus 3, which is going to give us 9 carbons. Moving on to hydrogens, I'm going to look at them with a different color. So we're going to have 1 hydrogen up the top here. We're going to have 3 more down here on the right hand side, and then we have our benzene ring. Now traditionally benzene rings are going to have their 6 hydrogens in them as well, so just write that down here. The formula for our benzene ring is going to be C6H6, but because this benzene ring isn't on its own, it's actually bonded to these 2 little branches that we have, there actually isn't the same number of hydrogens associated. Instead of having 6 hydrogens, there's actually only going to be 4 because we have these 2 branches. So what we're going to have is a hydrogen here, a hydrogen here, a hydrogen here, and a hydrogen here. But these 2 other places where the hydrogens would normally be are being taken up by these 2 branches. So in this case, what we're going to have is 4 hydrogens from the benzene ring, 1 from up top, so that gives us 5, and then 3 more from the right-hand side, so it's going to give us a total of 8. Finally, moving on to oxygens, this is the simple one. We're going to have 1 up here on the top left, another one on the top right, so that's 2. We have 1 here is 3, another one down the bottom is 4, and yeah, I think that's all of the oxygen. So benzene doesn't have any oxygen in it, which means that we don't have to worry about that one at all. So writing that down here, we have 9 carbons, 8 hydrogens, and 4 oxygens. Now we're going to find that relative molecular mass by adding these all together. So writing down that formula that we found earlier, the aspirin is going to have a formula of C9H8. 04. And what we're going to be using here is going to be, just to highlight them, we're going to be using carbon, we're going to be using hydrogen, which is up here, and we're also going to be using oxygen. So pulling up my calculator here, I'm going to add together all of the constituent parts. So we're going to have 9 hydrogens, so it's going to be 9 times, or I should say 9 carbons, so it's going to be 9 times 12. We're also going to have 8 hydrogens, which is 8 times 1, and we're also going to have 4 oxygens, which is 4 times 16. And that means that the total molecular weight here of the aspirin, the structure that we found, is going to be 180. So coming back to our question here, we've already found out that the total molecular, relative molecular mass, should I say, is going to be 180, which means that we can sub this into our formula here, and we're going to have 0.146 26 times 180 to give us the total mass. And in this case, if you plug that into your calculator, what you're going to find is the mass associated is going to be 26.28 grams of aspirin. Another thing to note here is we're being asked to calculate the average daily dose as it's written here. So we know that this person took 26.28 grams of aspirin over 365 days. So let's convert that into, what's the average daily dose, to divide that by the number of days, and that should give us the daily mass, and then we need to convert that to milligrams. So just writing that down at the bottom here, we're going to have 26.28 grams divided by 365 is going to give me a value of 0.072 grams per day. And if you want to convert that, and I'll just write it in a different color, if you want to convert that to milligrams, you multiply that by 1,000, and there's 1,000 milligrams in a gram, and that means that we're going to get 72 milligrams as our daily dose. And this was kind of a little bit more of a difficult question because you have to be able to count up all of the constituent parts of the molecule. But either way, there was a total of 6 marks going for this question, and the breakdown was fairly simple. You got 3 marks for correctly getting the mass of aspirin that the person took over the whole year. You then got 2 marks for correctly, just drawing it out there, you got 2 marks for correctly dividing that by 365 because we wanted to find the daily dose, and then you got a final 1 mark for converting that to milligrams. Moving on to part L here, this is kind of like the final question on this question 4 here. So this is going to be a little bit of a different question because we actually have 2 questions that you can do almost inside of this one, and these are normally based on the optional chapters that you do, or optional parts of the course, and in this case we have part A or B, so we're going to be doing both, and let's have a look at part A first. So with regards to part A, we are asked to write balanced equations to show the dissociation of carbonic acid in water to form first hydrocarbonate ions and then carbonate ions. So this is going to be a series of balanced equations that we need to write out here, showing this dissociation in order to get our full marks. And just having a quick kind of glance over part B, we're asked about iodine and how it's an example of molecular crystal, and we're asked a little bit more about crystals, but we will have a look at that one when we're finished part A. So part A here, we were asked to write the balanced equations to show this dissociation of carbonic acid. Now personally, I like to kind of do all of the equations at once. They kind of help me, it's easier to remember, like the system almost more than the individual ones. So first of all, I'm going to write down the formula and the equation, should I say, that shows how carbonic acid is actually created. So carbonic acid occurs when CO2, or carbon dioxide, mixes with H2O, and then this in turn turns into carbonic acid, which is going to be H2CO3. Now this isn't explicitly required in order to get your full marks, but personally I find it a little easier to remember than just remembering the formula for carbonic acid. Moving on to that, we now need to show how it dissociates in water to form first a hydrocarbonate ion and then carbonate ions, just kind of plain old carbonate ions. So then we need to show how it dissociates to form first that hydrogen carbonate. So what we're going to have is our carbonic acid to start with, so that's going to be H2CO3, and what we were told is that that's going to be mixed with water when it dissociates. So we're going to mix that with a little bit of water, so H2O. And what's going to occur here is there's going to be a dissociation. So that dissociation kind of looks like this. So what we're going to have is our HCO3 minus is created and our hydronium ion, which is a H3O plus. And what we can actually see here is that carbonic acid here on the left hand side, what's happening is it's dissociating, and a hydrogen is kind of being pulled away from it. And you'll notice here that here we have 2 hydrogens, but over here we actually only have this 1 hydrogen here, and that's kind of why we also have this negative charge here, is because when we take away one of those plus charged hydrogens from this stable net kind of neutral kind of arrangement, what you're going to have is this negative charge left over. So when we mix the water with that weak carbonic, or just kind of carbonic acid, what's going to happen is one of the hydrogens is ripped away from the carbonic acid, and we get a hydrogen carbonate, so HCO3 here being our HCO3 minus is going to be our hydrogen carbonate, and then that hydrogen is going to join on to the water, giving us our hydronium ion, or our H3O plus. The second half of the question was asking us to then show it, the equation continuing and then creating just a normal carbonate ion. So the way that we're going to show that is we're going to take what we got from like the previous question. So in that case, we're going to take our hydrocarbonate, which is going to be HCO3 minus. And similarly, again, this is going to be mixed with the same little bit of water, so H2O, and we're going to have this reaction occurring. So what's going to be happening here is, much like the carbonic acid in the first one, it dissociating, a hydrogen being ripped off here, we're going to be doing the same thing for this to get to the carbonate ion. So what we're going to be doing here is taking this one hydrogen here in the hydrogen carbonate and ripping it off. So we're going to have, and once we take away that hydrogen, we're going to be left with just CO3, and instead of just being minus now, we have 2 minus, and then that hydrogen is going to once again join on to the water to give us a, oh actually sorry, that's just the formula for water, so it's going to be joining on, that hydrogen is going to be joining onto the water to give us H3O plus, which in turn is the hydronium ion, similar to like the first question. So they're kind of like almost the same, they're the same like system, same rules, same kind of, all that's changing is, you know, it's going from a carbonic acid to a hydrocarbonate and then just to a normal carbonate. And yeah, that's going to be the correct balanced equations that are required here to get your full marks. So for part A, there was a total of 6 marks going, and the breakdown was fairly simple. You got 3 marks for first writing out the system of equations required to show the dissociation of the carbonic acid to create hydrogen carbonate, and then you got another 3 marks for showing how that hydrogen carbonate then went on to dissociate further in the water to create just carbonate. And either way, you know, this first line that I have up the top is just kind of something I use, a little bit of peace of mind to remind me that I have the right formula for carbonic acid. Moving on to part B here. So we've just kind of tackled part A. We're going to be looking at part B, which we said earlier is going to be working with these molecular crystals. You know, in particular, we were looking at this iodine I2, and we were saying that this is an example of a molecular crystal. But the real question that we're being asked here is what actually distinguishes molecular crystals from other types of other types of crystals. And this is just a nice wee piece of theory. It's just a few lines that we can write down. So there's no, it's actually not too bad. So let's have a look at that answer now. So having a look at the answer required for part B here, the distinguishing between molecular crystals and normal crystals is centered around lattice points. So in this case, molecular crystals have molecules that are going to occupy lattice points in particular. And kind of another important thing to note when talking about the difference here between a molecular crystal and just kind of a generic normal crystal is that these molecular crystals are actually going to be held together by van der Waals forces or any other form of intermolecular forces. So you could say anything like London, London forces, dipole-dipole interactions, hydrogen forces, hydrogen bonds, all of that also works. But in this case, I was just kind of saying van der Waals forces, van der Waals bonds, all of that. You know, the real takeaway is that molecular crystals are distinguished by the fact that they have molecules that are going to occupy lattice points, and they also are held together by intermolecular forces. In my just example here, I'm saying van der Waals forces. Similarly to like all the other questions, there was a total of 6 marks going, and you got 3 marks for saying the point about these lattice points, saying that, you know, the molecules occupy at these lattice points, and then you got another 3 marks for mentioning the intermolecular forces required to hold together the whole thing. So yeah, that's how you get your 6 marks for this part L.